So in all of this discussion, we keep talking about the entropy or randomness and the number of ways that something can be. And so let's dig in a little bit more to that entropy is related to this idea of probability. And so the probability that a particular arrangement could occur. And the more different possible arrangements, the more randomness. You can think about that in this diagram of the CO molecules down at the bottom. There's only one possible structure where all of the CO molecules are in the heads-up position. So that's perfectly ordered. There are fewer, it is less probable that that would happen. Versus if the 20 molecules, some are in the heads position and some are in the tails position, it is much more likely that we would get some arrangement where 9 are heads and 11 are tails. Okay, so relating the number of ways that something could be distributed, or microstates, so W here is the number of microstates, where each of these configurations, A and B, represent a microstate, a specific configuration. So that entropy is related to the number of microstates according to Boltzmann's equation here, that S equals Kb, Boltzmann's constant, which relates energy and temperature, and times the natural log of the number of possible microstates. So, kind of fun story, Boltzmann works this out in about the 1850s, when we're still not really sure that atoms are real. So Boltzmann was really a staunch advocate of atomism and made a lot of contributions to kinetic molecular theory. He also really struggled with depression and anxiety pretty much his whole adult life. And so I think that I kind of lift Boltzmann up as a model of, even people who might be struggling with their mental health can make really strong contributions to science. Boltzmann's mental health journey ultimately ended in taking his own life when he was about 60. And so I often wonder what other contributions Boltzmann could have made if he'd had better mental health support. And so I encourage you at this moment to take care of yourselves and to realize that mental health is important and that you have more to contribute. Okay, so thinking a little bit more about this idea of probability. Let's imagine we have molecules of an ideal gas that can move among 3 different bulbs labeled A and B and C that have equal volume. So they're connected where the molecules can get between them. So let's determine the number of microstates, the number of ways that we could have 2 molecules in bulb A. So it turns out there's only one way to get 2 molecules in bulb A, and that's to have molecule 1 and molecule 2 both in bulb A. Okay, now let's imagine that those 2 molecules can be randomly distributed between bulbs A, B, and C. Alright, so if we think about the possibilities there, we can have molecule 1 in A. Oops. Come on. We can have, and molecule 2 is also in A. We can have molecule 1 in B, and molecule 2 is also in B. We can have molecule 1 in C, and molecule 2 is also in C. We could also have molecule 1 in A, and molecule 2 in C, and we can have the reverse of that, where we can have the blue molecule here, molecule 1, and in C, and the yellow molecule in A. Okay, and then we can do that for the other permutations, where we can have one in A and the other one in B, or the blue molecule in A and the yellow molecule in B. And then the last combination here, we can have the yellow molecule in B and the blue molecule in C, or we can have the blue molecule in B and the yellow molecule in C. Okay, so when we count all of that up, we get both in A, both in B, both in C, A and C, A and C, A and B, A and B, B and C, B and C. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 ways that 2 molecules can be randomly distributed between bulbs A, B, and C. And so coming up with a way to do that systematically where we don't have to count them every time is the number of microstates equals the number of possible places to the power of the number of particles or molecules. So here in our system, we had 3 possible places to the power of 2 molecules, and that gave us 9. Okay, so we can then use Boltzmann's equation to calculate the entropy of having 2 molecules randomly distributed in bulbs A, B, and C. So we said that Boltzmann's equation is that entropy equals Boltzmann's constant times the natural log of the number of microstates. And so here we've got Boltzmann's constant is 1.38 times 10 to the negative 23rd joules per Kelvin times the natural log, we said the number of microstates is 9. And so we do the math on that. We get that the entropy is, I get 3 times 10 to the negative 23rd joules per Kelvin. Okay, but 2 molecules is almost never the thing we care about. So let's imagine we can calculate the entropy of 1 mole of molecules randomly distributed in bulbs A, B, and C. So in that case, again, we have that entropy equals Boltzmann's constant times the ln of the number of microstates, and so we get 1.38 times 10 to the negative 23rd joules per Kelvin times the natural log of, 1 mole of molecules in 3 bulbs. So that's going to be the natural log of 3 possible places to the power of 1 mole of molecules. So if you try to do this on your calculator, you might get an overflow error because 3 times 6.022 times 10 to the 23rd is too big for your calculator to process. So here we need to use another log rule that log of y to the x power is the same as x times ln of y. So we're going to bring that Avogadro's number out of the log thing, 1.38 times 10 to the negative 23rd joules per Kelvin times 6.022 times 10 to the 23rd per mole times the natural log of 3. And if we do that, I get 9.13 joules per mole times Kelvin. Okay, can we use Boltzmann's equation to calculate the entropy of a mole of molecules, but all of them in bulb A instead of randomly distributed? So if we, again, use Boltzmann's equation, S equals Kb times the natural log of the number of ways, we have 1.38 times 10 to the negative 23rd joules per Kelvin times the natural log, we need the number of microstates. So remember we said that for all of the molecules to be, I'm sorry guys, let's try this again. So S equals Kb times ln of W, 1.38 times 10 to the negative 23rd joules per Kelvin times ln, and we need the number of microstates. We said if they're all going to be in bulb A, there's only one way to get them all to do that. So this would be the ln of 1. ln of 1 turns out to be 0. So the entropy of all of them in one place is going to be 0. Okay, and so here again, we can find we said that we very rarely actually talk about entropy directly. Instead, we're usually more interested in entropy changes. So we could also use this formula to calculate how entropy changes as the gas expands from bulb A to bulb C. Okay, we said that delta S equals Boltzmann's constant times the natural log of the number of ways final divided by the number of ways initial, the number of microstates. Okay, so we know Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin. And so then we can figure out the number of microstates. So we said that finally the number of microstates would be 3 to the power of Avogadro's number divided by 3 to the power of, times divided by 1, because there's only one way to get them all in bulb 1. There's only one place for them to be. So 1 times to the 6.022 times 10 to the 23rd power, which is 1. And so if we do that, we once again have to move the Avogadro's number out, 1.38 times 10 to the negative 23rd joules per Kelvin times 6.022 times 10 to the 23rd per mole times ln of 3. And if we do that, we once again get 9.13 joules per mole per Kelvin, because the final was 9.13 minus 0, the initial, when they were all in one bulb. You'll notice that we end up multiplying Boltzmann's constant times Avogadro's number a lot. And so if we look at that in a little bit more detail, you'll see that Boltzmann's constant, so Kb times n Avogadro, equals, we got 1.38 times 10 to the negative 23rd joules per Kelvin times 6.022 times 10 to the 23rd per mole. And if you multiply that out, you find that you get 8.31 joules per mole times Kelvin. And so it turns out that Boltzmann's constant, the relationship between joules, energy, and temperature, Kelvin, times the number of molecules in a mole, gets you R, the ideal gas constant.